Okay, this is just a video on Activity 1, Linear versus Nonlinear Relations from Unit 3, Analytic Geometry. Okay, so I'm just going to try to summarize this in another video, which may sound exactly like the other one I made, but we shall see. Okay, so I'm on the first page of the Linear Relation, or Activity 1 content, and it has you graph a whole bunch of equations, so I just took 6 of them. So it has you graph them just so you can see what they look like. So if we're going to graph all of these, then y equals x, if you make a graph of that, let's just make ourselves a couple little grids here, and we'll just draw some rough sketches, which I said you could do by using Desmos and just typing them in and seeing what they look like. So you'll notice this guy makes a straight line. Y equals x squared makes what we call a parabola. Y equals x cubed actually does this kind of thing. Y equals 4x minus 1 is going to do something like this-ish. And y equals negative 2 is going to do something like this. And x equals 9 is going to do something like this. So when you graph all these, I just wanted you to make conclusions about the shapes of the graph. So one thing you'll notice right off the bat is the things that are forming the straight lines, like just try to draw some similarities between their equations. So all of these 4 equations make straight lines. And what I'm noticing about them is they don't have any exponents compared with this one and this one. That's what jumps out at me right off the bat. So like all the yellow highlighted ones, they just have most of them just have like a y and an x and some numbers, but no exponents at all. And yeah, no other like oddball things. So whereas these 2 green ones, this guy has an exponent of 2 and this one has an exponent of 3. So that's what the first little activity wanted you to notice. And we referred to the kind of largest exponent as the degree of a function or a relation, as the degree of it. So if I wanted to comment on like, what's the degree of y equals x? What I do is I look at the x value and look at the exponent on the x. And there's actually an exponent of 1. Technically, we don't write it. So I would say this function has a degree of 1. Whereas when I look at this guy, the x has an exponent of 2. So I would say this guy has a degree of 2. And this one has a degree of 3. So it turns out all linear relations, so all the linear ones, the straight lines, will have a degree of 1. And if there's multiple exponents, you just look at the biggest one in the expression or equation. Okay, there we go. Okay, so take these 2 equations, for example. If we wanted to figure out what's the degree of this first equation, equation number 1 here, I would see like this guy has an exponent 4, this one has an exponent 2, and technically that has an exponent 1. So you're just going to look at the biggest exponent, and that's what the degree is going to be. So this guy is going to have a degree of 4. If we look at the second equation, there's just one x value, and it doesn't look like it has an exponent, but technically it has an exponent of 1. So we would say this has a degree of 1. And degrees of 1 we know are going to make straight lines. They're going to be linear. Whereas a degree of 4 is not. It's actually going to make some crazy curvy thing, which you don't find out about until grade 12. I think like some of these weird ones here, where, okay, this one has, I didn't talk about them, but this one has an x, which has a 1, so like, I guess we can kind of confirm this would be a degree of 1, and so this one, degree of 1, but like, this one doesn't even have an x in it, so it's kind of weird, but it's just because it's this flat line, but you know what, we're going to also call this a degree of 1, I think. I don't actually know, but I would assume. Okay, So that's basically what the degree is. It's just the largest exponent on the equation, on the x value. And the other conclusion we wanted to make was that if there's a degree of 1, it means your function or your relation is going to be linear. Okay, next we talked about different forms of a linear equation. So there's a different way to write linear equations, and you should be familiar with them all. So the first way we learn is called slope-intercept form. And it looks like this. It's like probably the most common one. And we say y equals mx plus b. So it's called slope-intercept form because we can easily identify the slope, which is this m variable, and the y-intercept, which is this b variable. So when things are in slope-intercept form, when straight lines, like linear relations, are in slope-intercept form, you can tell because this y over here is on its own, so there's a solo y there. And then there's a defined like x variable with a number out front and a number on its own. That b guy is just a number on its own. So that's kind of how we tell it's in slope-intercept form. Okay, so if we had to identify the slope and y-intercept from these equations, well, they're just in slope-intercept form. I can tell because the y is isolated over here, and then there's like kind of two terms. So I can easily tell that this 3 is the slope because I know it's always in front of the x, and this guy is the y-intercept, and it would actually be a -1 since it's -1 there. For the next one, I'm noticing that my slope would be -1/2. That's the coefficient in front of x. And my y-intercept would be +4. This guy is still in slope-intercept form. It's just there's only one term because there's no y-intercept. So this guy has a slope of 7 and a y-intercept of 0. Because technically you'd have that +0 there. So that's how you find the slope and y-intercept. Also, if you just had a y-intercept, so if it was like y equals 10, now there's no slope. But I guess it would kind of still be in slope-intercept form. So you would know that your slope, in this case your slope is actually 0, and 10 is your y-intercept. Okay, moving on. There's another version called standard form that you can write equations in. Less popular, but apparently important. It's called standard form. And it's written with every single variable on one side, and then it's equal to 0. And another thing to note is that this variable a is always positive in standard form. So let me write you an example. So let's say I did like 3x plus y minus 5 equals 0. That would be in standard form. Or 2x minus 4y plus 1 equals 0. Also standard form. So they just take every variable in the equation and they put it all on one side of the equation. It can also be written the other way. So it could be like 0 equals 2x minus 4y plus 1. So often we don't have like a lot of use for standard form because, we're not really sure what those numbers represent. They're not really the slope or the y-intercepts because y is not isolated. So like it's harder to identify. But it does have its uses, which we shall find out. Hopefully. Okay, so what's really handy is if you can convert between the two forms. Because as we saw, standard form might not be super useful. So let's make an equation in standard form. So 2x plus 4y minus 12 equals 0. So this equation's in standard form. That's what we call it when it looks like that. And we want to know what the slope and the y-intercept. So we want to convert it into slope-intercept form. And we know that slope-intercept form looks like y equals mx plus b. So our goal is to isolate y, basically. We want to get y alone. So we take this giant equation, and I know I want this 4y to remain on the left-hand side. So I'm actually going to subtract 2x and add 12 to both sides so that I'm just left with a 4y on the left. So however you solve equations, I'm going to subtract 2x and I'm going to add 12 because I know that will get rid of those two things. But then whenever I do to one side of the equation, I have to do to the other side of the equation. So I'm also going to do it over there. So now on the right side, I have minus 2x plus 12. I don't bother writing the 0 because 0 plus 12, that's just going to be 0. 12. Ah. Okay, so then we're almost there. We just have this 4 in front of the y that we need to get rid of. So I know I can get rid of it. Right now it's being multiplied by y. So I know if I divide each term by 4, I can actually cancel those 4's out because 4 divided by 4 is just 1. So I'm just left with 1y. And then I just go ahead and simplify the right. So negative 2 over 4x, I could simplify to negative half x because 2 divided by 4 is going to be 0.5, but I don't really want a decimal, so I'll just put it in lowest terms, plus 12 divided by 4, which is 3. So there you go. Now we have stuck it into slope-intercept form, which is so much more handier because now we can tell that's the slope and positive 3 is the y-intercept. So it's handy to be able to convert from one form to the other. Now if we wanted to convert into standard form for some reason, so let's say we had slope-intercept form, we had y equals 3x plus 5, and we wanted to convert that to standard form. All we're going to do is make sure all the variables are on one side of the equation. So I actually think I'm just going to move my y to that side. And to move it over, that means I'm going to subtract y on both sides. So y minus y is 0. I know I want, in standard form, I want my x to go first. Then I want my y, so I have a minus y. Then I want my number, plus 5. So that's kind of how you just convert from slope-intercept form into standard form. You just kind of move everything to one side, whichever side you want. And it's always important to make sure this first guy, A, is positive. It's always good to make that positive. Just some extras, in case you want to know this. Let's say you had a slope-intercept form that was like y equals a half x minus 4. And you wanted to convert that into standard form. I just wanted to show you something. So just like the previous example, maybe we want to move the y to the other side. So we're going to subtract y on both sides, which is a good idea. So we get 0 equals a half x, and then I'm going to put my minus y minus 4. So all I did was move the y to the other side, and it became a negative y because I subtracted it actually. Okay, so that's standard form, except here's a little extra, which you may hate. If you don't want to have fractions in standard form, you could get rid of them. It actually is what most people do. So to get rid of this 1/2 fraction, I know that if I multiply every term by 2, I know that that will get rid of a half, because I know that 1/2 times 2 is equal to 1. So I'm using that knowledge to say if I multiply everything in this equation by 2, so like literally, you multiply this whole equation by 2. The left side, the right side, every term by 2. You can do that, and it will still be the same equation. So 0 times 2 is still 0. A half times 2 is 1. Negative y times 2 is negative 2y. And negative 4 times 2 is negative 8. Then this would be your standard form. So I just took this and converted it into this, basically just to make it look nicer, because it looks way nicer than starting your standard form off with a fraction. Okay, so that's basically everything in activity 1. Hope it helps.